Let's continue on talking about how astronomers can find extrasolar planets by looking at the Doppler technique. Remember that we're thinking about the fact that as a planet orbits its star, the star is actually undergoing a motion as well. They're both moving around their common center of mass. Depending on our viewpoint, as that star wobbles, we can see its starlight that comes towards us either being blue shifted or red shifted as it moves towards us and away from us. That's the basis of the Doppler technique. This has been used for the majority of the planet discoveries. So we have to remember the Doppler technique and remember that the Doppler shift is related to relative motion between the emitter of the light and the observer of the light. And as there's a motion towards each other, you see the light shift towards the blue end of the spectrum, and as it moves away, you see it shift towards the red end of the spectrum. The amount of that shift is directly related to this relative speeds, so the faster it's moving towards us, the larger shift we're going to see. Now, because of the fact that the star, if it's moving in a circle, will have different components of speed towards us and away from us. In fact, when it's at this point in its orbit and also here, it's moving in a line perpendicular to our line of sight, and so we actually don't see any Doppler shift at all. We only see it as it's moving towards us and away from us. So we see this gradual change over time. And as this happens, you actually get different speeds towards us and away from us. This is going to go through some periodical repeating because of the fact that the star is going through a complete orbit. So as we go from here to about here, it's gone through about one complete period, or as you can see, it's somewhere around a period of, say, 4 days. So that means that both the planet and the star have an orbital period of about 4 days. Now, the types of things that we can find out from this is the amount of velocity, or the maximum velocity that the star attains, can give us a sense of how fast how massive the planet is. It also allows us, because we can use Kepler's third law, we can find a relationship between the period and the distance from the planet to the star. So it's actually kind of interesting, all the information we can get from this Doppler shift. Here are some different graphs of different stars, and you can see sort of how the Doppler curve is changing depending on different things. So for instance, in this curve, we have a star that's almost the mass of Jupiter with a distance of about 1.7 astronomical units, and so this is what the curve looks like. If we put a more massive planet in the same orbit, the period would stay the same, but the velocity shift, the maximum velocity would increase, and so you'd get higher peaks. And so as we go from here to here, we're just changing from a smaller, less massive planet to a larger, more massive planet in the same orbit. If we move the planet into a closer orbit, because it's closer, it has a greater effect gravitationally on the star, so the wobble is going to be bigger. So in this case, two things are going to change. As we go from here to here and we move it closer in, we get a higher peaks in our curve, and of course, because it's closer now, the period is going to shorten from Kepler's law. You might remember that the Earth's planets are a little bit eccentric, and all these pictures are very symmetric and sort of illustrate more of a circular orbit. The curve becomes a little skewed when you have a more eccentric orbit, as we see in this graph. Now, the Doppler effect isn't perfect because we have to have some sort of motion towards us and away from us. If we were viewing the orbit from, like, say, this is what it looked like us, and it was a plane perpendicular to our line of sight, we wouldn't see any Doppler effect at all, and therefore we wouldn't even be able to say anything about the motion of the star. However, if it's perfectly perpendicular to us, we measure the total motion and Doppler shift. But if it's somewhere between being right along our line of sight and perpendicular to it, we're only seeing sort of a portion of the motion. Therefore, a lot of times when we have the Doppler technique and we get some results, it's really just an estimate. It might give us the upper measurement of the mass of the star, etc. Another thing that we can use to study extrasolar planets are the transits and eclipses. And this is basically when we're looking for changes in the star's brightness when the planet passes either in front of or behind the star. Basically, of course, then this is only going to work if we're looking at the orbit as viewed edge-on from Earth so that we can actually see it pass in front of the star. And basically, by seeing how much the light dims is going to give us a sense of how large in size the planet is. And when I say that, I mean its dimensions, like its radius. Because sometimes stars will actually vary in their brightness anyway, you have to really look for this and see that it's repeating in a very predictable way to establish that the changes in brightness is due to the transit of a planet instead of just something going on with the star. Here's a picture showing a planet passing in front of a star and the dimming in the star's light that we might observe. We also might see by looking at the spectrum and the intensity of this light, we might be able to learn something about the planet's atmosphere as well. So the strength and weakness of the transit technique is you can actually detect smaller planets with this than the other techniques because very small planets don't induce a very large wobble, and so that makes the Doppler technique not as effective. You can do this with small or large telescopes. However, you have to have really a perfect viewpoint so that you're viewing the planet star system edge-on relative to the Earth. It's also easier to use if the planet's period is relatively short, so you can repeat your observations over and over and be sure that what you're seeing is due to the motion of a planet and not just changes in a star's light. Basically, what we hope to learn about our search for extrasolar planets is to give us more insight into our own solar system. We found that in our solar system we have terrestrial and Jovian planets. Are there other types of planets, or are they always limited to these two categories? Is our solar system like others, or is it very unique? Can other solar systems be explained by the nebular theory, or do we need to review that or change it a little? So far, most of the planets that we have found have orbits relatively close to their star, which makes sense because those are going to be the easiest ones to detect. Most of the orbits are rather eccentric, and at least 30 stars have 2 or more planets, and at least 5 systems have been found to have planets in orbital resonance. Here's a picture from your book just showing the different types of planets that have been found. You're gonna see that most of the planets, as expected, are actually very, very large, which makes sense because the effects of a very large planet are much easier to detect than that of an Earth-like planet. We've actually found that most of the planets seem to have more in common with Jupiter than they do with Earth. So, there's not a lot found in that are like Earth. So it's a little confusing why all these systems that we're finding have Jupiter-like planets that are very close to their stars, because we would expect terrestrial planets to be closer to the Sun with the Jovian planets further out. We found really something that's not quite like that. So we have to re-examine the nebular theory. Do we need to discard it? Doesn't seem like that's necessary. What astronomers think have happened is the Jovian planets formed further out, as we have observed in our solar system, but they think that maybe what they're doing is undergoing some sort of planetary migration or have had gravitational interactions with other objects that have pulled them in closer to their stars. And you can read more about the planetary migration in your text. And that's it for now.